let's now look at how to actually encode quantum states in a photon, and we'll typically describe them using terms such as single rail, dual rail, or multi-rail encodings. In the case of single rail encoding, the state is represented by the presence or absence of a photon, and this would correspond to the state 0 and 1, and a superposition of these states is also possible, and that represents the generic qubit. This can also be generalized to qubits, that is, which have higher dimensions. And here, the higher number states with more than one photon would come into picture. So, to summarize that, a single mode with multiple number states can encode a qubit or qubit in a single rail encoding. When it comes to dual and multi-rail encoding, we talk about the photon always being present, but can occupy one of the two orthogonal modes or more than two orthogonal modes, say two distinct polarizations of the qubit or two distinct time bins. And they can form a qubit with superposition of these orthogonal modes as well. And that is where the encoding of dual or multi-rail fall under. And with that, I would also like to discuss which of these encodings would relate to the degrees of freedom and how they would be more relevant for fiber optic communication. We have talked about some encoding schemes. It could be time bin, frequency bin, polarization, path, and orbital angular momentum as well. Among these encodings, the time, frequency bin, and polarization are the most practical for transmission through single mode fiber. And this is important because single mode fiber is the backbone for like today's telecommunication networks. And light in single mode fiber is confined to a single spatial mode. Uh, this means that spatial encodings like orbital angular momentum may not be compatible, as well as path encoding, which would need several stabilized path lengths that don't drift with time. That's easily more reliably implemented on integrated photonic or free space platforms rather than across long distance fiber links. So, with that, each encoding type has its own advantages and sensitivities, and understanding how they interact with environment noise will be something that is key to our later discussions as well.